Hello and welcome back, everybody. Today in geometry, we will be going over the section 9.3 and also 9.4, trying to nail two birds with one stone. Figure they're short enough, so why not just go ahead and make one video out of it. So in section 9.3, we will be talking about the converse of AIP and also CAP. So, just kind of flipping the letters around, and it's PAI and also PCA. So what that means is that if you have two lines that are parallel, then that means their alternate interior angles are going to be congruent to each other. And in addition to that, if the two lines are parallel, then that means their corresponding angles are going to be congruent to each other. So that's what we're going to be proving for today. Then in section 9.4, we're going to talk about the sum of the interior angles is equal to 180 degrees. That's something that we have kind of took for granted ever since we were introduced to geometry, like probably 2 years ago, or maybe even longer. But now we can actually go ahead and prove it as a theorem using everything that we know so far. So I just want to quickly reiterate, first of all, right now, as of for the time being, the only ways that we have to prove that two lines are parallel to each other would be one of three methods. So this is something that you might want to consider when you do a proof in your homework. Either one, you can do an indirect proof, which means that you assume the two lines are going to intersect each other, and you're going to get some sort of triangle that most likely does not make any sense. Or you can use AIP to say that if the alternate interior angles are congruent, then that means the two lines are parallel to each other. Or finally, we can use CAP, which says that if the corresponding angles are congruent, then that means that the two lines that are cut by the transversal are going to be parallel to each other. So those are the only three ways for the time being. All right, now let's go ahead and talk about the converse of those theorems, PAI and also PCA. So first one is going to be labeled as Theorem 9.9, which is the converse of AIP. So we call it PAI. So again, that means that if the two lines are parallel to each other, then that means that their alternate interior angles are going to be congruent to each other. So here's this picture on the right, and you can see the given as what is if, which is the two lines are parallel to each other. The conclusion is that 1 and 2 over here, you can see, are going to be equal to each other. Well, we're going to go ahead and do this one indirectly. So because, indirect proof seems like it's something that's been working so far. So why not just go ahead and keep with it? So we're going to go ahead and, like we said, do an indirect proof. We're going to do it by doing the following. We're going to assume that angle 1 does not equal to the measurement of angle 2. So that means that they're not equal to each other. Now, according to trichotomy, it's probably the case that if they're not equal to each other, then one is bigger than the other, or one is smaller than the other. So it's always going to be one of those then. So let's just go ahead and say that for the time being, angle 1 is going to be bigger then. So over here, let me just kind of write that. So this is going to be bigger. And then that means that angle 2 is going to be smaller. Okay. Now, in that case, what I can do is the following. If angle 1 is bigger than angle 2, then what I can do is I can form, I guess, something that's like angle x, where the measurement of angle x is equal to the measurement of angle 2. Okay, since it's a bigger piece by parts theorem, I can go ahead and slice it a little bit. So then that way you have an angle that is going to be congruent to the smaller piece. Now, over there, since angle x is going to be congruent to angle 2 by this this construction that I made, then that means that I can now go ahead and use AIP in this case, right? To form a line that is going to be parallel to line 2. So this line right here, we're going to go ahead and call it R. According to AIP, R should be parallel to line 2. But right there, that is a contradiction, because if you notice, R being parallel to line 2 at this single point, and then line 1 is also going to be parallel to line 2 at that single point. And if you recall, there is an there is a uniqueness theorem that says that through an external point, there can exist only one parallel line that contains the point that is parallel to the line that's given. So that's going to be our contradiction then. All right, so now let's go ahead and look at the other one, which is going to be Theorem 9.10, the converse of CAP, which is going to be called PCA. So this time around, what's going to happen is that, again, the two lines are going to be parallel to each other. I want to conclude that 3 and 4, the corresponding angles over here, are going to be congruent to each other. Well, the easiest way I can do this is why don't we go ahead and use the previous theorem, because that's probably the best thing to do, right? That's why we prove these things in a certain sequence. Looking at angle 3, the location of it, I noticed that there is a vertical angle which we can call angle 1. So by vertical angle theorem, then we can say the measurement of angle 1 is equal to the measurement of angle 4. And if you notice the location of 1 and in comparison to the angle 4 over there, they are alternate interior angles. So then now, by what we just proved, theorem 9.9, since that these two angles right here are congruent to each other, then that means that the two lines are going to be parallel then as a result, because we have alternate interior angles that are congruent. So therefore, it's going L1 and L2 are parallel to each other. All right, so now we've got through all the hard parts, and then everything else is going to be hopefully, just pretty straightforward and easy. Now, there are some other theorems that are very minor, but, the ones that we pointed out that are in red, if you haven't noticed already, those are the very important one. AIP, PAI, PCA, and then also CAP. The rest of these are just very minor theorems. So here in theorem 9.11 and 9.12, we're just going to go ahead and quickly talk about them. And then the proof of it, well, you can probably prove them on your own, or you can actually, take a look at the book. But, for the most part, they will most likely not be used in the book. So here's the first one then. If you have a plane, if in a plane, if two lines are parallel to the third one, then those two lines are going to be parallel to each other. So here, if I just draw a picture so you can see what's actually happening, we're basically saying the following right here. Let's say that we have L1 over here, L2 over here, and L3 over here. If that L1 is parallel to L2, and also L2 is parallel to L3, then the result is that L1 is going to be parallel to L3. So in other words, it's kind of like the transitive property for parallel lines then. So if one is parallel to the second, and the second is parallel to the third, then the result is that the first is parallel to the third then. Next, afterwards, in theorem 9.12, it says that in the same plane, or different plane actually, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the second line. So once again, let me just go ahead and draw a picture. So here we're given that we have one line right here, we'll call L1. This is going to be perpendicular to that line. We're going to go ahead and call that T then, for the sake of, quote unquote, using a transversal. We also know that L2, which is down here, and we're told that L1 is parallel to L2. So that right there is going to be part of my if statement. In addition, T is going to be perpendicular to L1. Well, the conclusion out of this is that what we want to get is that T, as you can see, is going to be perpendicular to L2. So that right there is going to be the theorem right there. Okay, so pretty trivial for the most part, but hopefully you can understand where that's coming from. Okay, so now let's go ahead and move into 9.4, which is the very important theorem that you guys can all been waiting for, because, well, this is something that we can finally prove after all this time. So here it is, theorem 9.13. It says that the sum of the three angles inside any triangle is equal to 180 degrees. So in our picture over here, you'll notice that we have three angles inside this triangle ABC. And what I would like to do is prove that the measurement of 1, 2, and 3, the sum of them is equal to 180 degrees. Now, the proof of this, it might not be very obvious because we need to introduce something. And in terms of what that something is, it's probably going to have to do with the parallel lines that we've been talking about. So here it is. The proof is going to be starting with introduce the line L, which is going to contain point C, and it's parallel to AB. So according to theorem 9-3, which says that if you have an external point, there is exactly one line that is parallel to it to the line that's given. So using a blue pen, let me go ahead and draw that line that I'm going to introduce in this case. And this is the guy that I'm talking about. Over here, we're going to go ahead and call it line L. And according to what's said is that this line L is supposed to be parallel to AB, the line that's below. So note what's happening now is that I have created a few more angles. So let me go ahead and introduce them. Let me go ahead and call this out here number 4. And then this out here is number 5. And in addition to what we have in the picture, you can probably see that there are some alternate interior angles, well, just alternate interior angles, if anything. Okay. Now, this is something that's kind of unique. If you look at 4, 3, and 5, the angles, you'll notice that they form kind of like a linear, not pair, but linear quadruplets. And that right there, you can go ahead and, show by using linear pair and then angle addition postulates, and then breaking it into parts. But nonetheless, according to this picture, we can see that the measurement of angle 4 plus the measurement of angle 3 plus the measurement of angle 5 is definitely equal to 180 degrees. Well, now let's go ahead and use what we've been learning this entire time. Look at where 4 is located. Whoops, don't want to erase that. So let me go ahead and erase this part over here. Getting a little too excited, I suppose. Look at where 4 is located, right? And look at where 1 is located. They are alternate interior angle. Because L, the line that we created, is parallel to AB, then that means that 4 and 1 are going to be congruent to each other. So I can go ahead and replace this equation with measurement of angle 4 with the measurement of angle 1. In addition to that, we can go ahead and look at angle 5 and also angle 2 over here. They are also alternate interior angles, and they should be parallel because they should be congruent because L is parallel to AB. So that is to say over here, I am going to now say that the measurement of angle 5 gets replaced with the measurement of angle 2. Measurement of angle 3, we'll just go ahead and keep it as is because it's part of the triangle. And right there is your proof then. Now we know that the sum of all the interior angles in any triangle will be 180 degrees. All right, now for the minor corollaries, which you can probably, kind of disregard for the most part because if you have this theorem 913, you can definitely just do the rest of it on your own. These corollaries are kind of nice to have if that situation ever comes up, but it's rarely the case. But anyhow, let's go ahead and quickly talk about them so you know what they are. The first one, which is going to be corollary 9-13.1, which says that if you have any triangle ABC and another triangle DEF, if it's the case where one angle is equal to the other, so A is congruent to D, and it's the case where the second angle is equal to the second angle in the other triangle, then the conclusion is that, well, you can probably conclude something about the third angle in the first triangle and the third angle in the second triangle. Those guys, angle C, is most likely going to be congruent to angle F in the other triangle then, okay? We can, again, prove it by using theorem 913 over here, where the sum of all the angles is equal to 100. Sum of all the interior angles is equal to 180 degrees. Next corollary over here, it says that if you have a triangle where angle B is going to be a right angle for that triangle ABC, then the other two angles are going to be what? Well, let me just go ahead and draw the picture for it so you can see what's happening. Here's your triangle ABC. B is known as the right angle. We have angle A over here and angle C right here. According to our theorem that we just proved, then that means that these two guys right here, they're probably going to be complementary to each other, meaning that the sum is equal to 90 degrees. So that is going to be conclusion over here. So they are going to be complement to each other then. Okay. And finally, for the last part over here, corollary 9-13.3. The exterior angle is equal to the sum of its remote interior. So this is a stronger version of the exterior angle theorem, because now we know that if you have a triangle and you look at the exterior angle over here, which we can call 1, you can call 2 and 3 over here, you'll notice, according to this corollary, the sum of the measurement of angle 1 is equal to the measurement of angle 2 plus the measurement of angle 3. The way we can prove that is draw the linear pair to angle 1 over here. So we'll go ahead and call that angle 4. And then from there, maybe you can do some sort of linear pair and also theorem 913 to say that they are all equal to 180 degrees and a little bit of algebra and see how that works out then. Okay. Okay, so let's go ahead and use Theorem 913 to do the following proof right here, because I would like to be able to see an example of this if possible, or at least show it to you guys anyways. In this picture right here, what I want to do is I want to prove that angle A, angle B, or the measurement of A and B, if I add the two together, the result is that is equal to the measurement of X plus the measurement of Y. So yeah, so that's basically the what I want to conclude. Well, if I'm going to use Theorem 913, I think what I need to do is maybe introduce some triangles so we can see how that works out. So here, I have two choices. You can see that I can probably create GK over here, the segment, or you can create MH over there, the segment. Now, looking at GK, if I create that, unfortunately, that doesn't look like it's going to work out because I noticed that A and B are screaming to be exterior angles, and it's not, and those are not going to be exterior angles according to triangle MGK or KHG. So that's probably going to be out of the question then. So let's go ahead and see if we can draw the other one and see how that works out then. So what I'm saying is maybe we can go ahead and introduce MH over here, right here. And now we can see that B is going to be the exterior angle of that triangle next to it. And A is going to be the exterior angle to that angle that's next to it. And just to make it a little bit easier, let's go ahead and call this angle 1. Let's go ahead and call this angle 2. Then let's go ahead and call this angle 3. And then let's go ahead and call this angle 4. All right, now, looks like we have an exterior angle and then we have some remote interior angle. So according to what we just showed in the corollary 9-13.3, we can say that the measurement of angle 1 plus the measurement of angle 3 is equal to the measurement of angle B. So that is going to be our first part. Well, we can also go a little bit further and say that the measurement of angle 2 plus the measurement of angle 4 is then equal to the measurement of angle A because of both of them, the corollary of 9-13.3. Well, they are basically parts of angle X and angle Y. And in order to see angle X and angle Y, I'm probably going to add these two equations together then. So then by addition property of equality, then we can say that A plus B on the right-hand side is equal to the measurement of 1 plus the measurement of 2 plus the measurement of 3 plus the measurement of 4. And finally, by angle addition postulate, you can see that 1 and 2, that comes out to be just plain old X. And then whereas 3 and 4, that comes out to be just plain old Y. And right there, that is going to be our proof then. All right, so thank you so much for watching, and yeah, now I'm going to go take a little break, and we'll come back to the next time around, all right? I'll take it easy. Goodbye.